then minus, right, comes in. And you get this molecule right here. Everyone understand the next one? This one will attack at H plus. H, now add on this carbon, you get a plus here, and you have an X over here. Everyone understand why you get a carbocation on that position? Because this is secondary, this is primary, so it's secondary, but hold on, there's an X there. I thought these halide groups pull electron density. This bromine or chlorine or whatever, I thought it pulls electron density. Yes, through the single bond, it can pull electron density, inductively, but it also has lone pairs, and the lone pairs can donate in, right? So even though it's a fluoride, iodine, whatever, it can donate in and stabilize. That's secondary carbocation. Does everyone understand that? You have a carbocation that's secondary. It always asks the question, can I spread out that plus charge? Can I spread out that lack of electrons? Right, so plus, it wants electrons. Well, there's a fluoride right there, or a chloride, or a bromide. It has lone pairs, it can donate in. So now the plus charge is between a carbon and, just say it's a fluorine. Carbon and the fluorine is going back. That's a lot better than just staying on the carbon in the secondary. Now it's spreading out over two atoms. That's a lot more stable, even though it's a halide. Okay. So this is the intermediate. Then your next X comes, bang, and you get the gem. That's why the X goes on the same carbon. Okay. Everybody all right with that? It's not that hard. It's an alkyne. It's just reacting, getting a plus charge. Halide comes in, does the second round, two equivalents of HX, and you get this gem over. Now what if we wanted to add more halides to it? Go to this terminal alkynes. Go to this terminal alkyne, you add X2. Now remember, when you have the alkene and you added X2, everyone would draw that, right? Cool? Yeah, the X2, you know it's going to form that three-member ring, the plus charge on it. This one and this one, and now the next X is going to attack. Which one is it going to attack? This position 1 or position 2? Which one? Or we're just doing alkene here. Position 1 or 2? Carbon 1 or carbon 2? This is carbon 1 or carbon 2? You have the second X minus, and it wants to come in and attack. Which one is it going to attack? Which one is it going to attack? This is a really easy question, you have to know this. Which one has a more delta plus? So that X on top is a plus charge, right? It's pulling electron density towards it. It has two bonds. Which bond do you think is pulling more electron density from? This is a secondary. This is a primary. It's definitely going to be pulling up here. This is a much bigger delta plus because it can handle it. So this X is going to come and attack right here. Right? Yes? You get it? You have to know this. This is kind of a review. We already did this chapter. Right? It forms this thing here. The X comes in. It's going to attack this position because this is not the same as this. This is primary. This is secondary. Here's two electrons, two electrons. This X is a plus charge. It is pulling on electron density as these two bonds of two electrons each. It's pulling. Which one is it going to pull more? It's going to pull more on the one that's attached to the secondary. Because a plus charge on the secondary is a hell of a lot more stable than the primary. So therefore, the next molecule that comes in, that's the biggest delta plus, and it's going to attack there. This is a much bigger delta plus than this one because it's secondary, so the X is going to go over over here and open it up. Here they happen to be the exact same groups, right? Or remember, we can do the bromine H2O. So you form the 3-member bromine ring, then the H2O then comes in. And the H2O, then you end up getting OH and the Br. But the OH, H2O always attacks the biggest carbocation. Okay. Here you don't see it, these are both X's. Okay. Now, back to the alkyne. Same thing. It goes through this type of intermediate, but there's still a double bond there. So it goes to the 3-member ring, X, and the X comes in, trans. Then the next X2 comes in, because it's still a double bond, it forms a 3-member ring, and it comes in, and basically you just saturate that double bond. You have that, triple bond, it's just gonna put all X's across it, all the way down to the single bond. Okay? So it just does 2 rounds of this 3-member ring thing. It does that, then it makes another 3-member ring, and it attacks again. Okay? So if you see a molecule like this, a tetrahalide across a single bond, with all these bromines or fluorines or whatever, you're like, oh, I know, I recognize that, it probably came from an alkyne, where I just added Br2 twice. Okay? Now here's the addition of HX and X2. Here's a triple bond. So we did all these reactions already with double bonds. Now we're just doing the same reaction with triple bonds. Now the problem is you have a triple bond, it does the same chemistry. You do the reaction, but when you do the reaction, that's cool, but you're left with still a double bond, so the double bond can still do more reacting. Okay. Here's a triple bond, you add HBr. This will attack the proton, you get the proton over here, and the bromine will come. So you add across the triple bond, you get the HBr. It's exactly the way it's supposed to go, it's just like if this is a double bond. But it's still a double bond. So we're gonna add another equivalent of HBr, same thing, this is gonna pick up H+. This is a more stable carbocation, and the bromine is gonna attack that position. There it is. Okay. And the reason it attacks that same position, that carbocation, because the bromine has lone pairs, can donate in. We talked about it a second ago. It's much more stable. Even though there's bromine there, it's still better than a primary carbocation. It comes in here. So you get this type of structure. Geminal bromides, or halides. So that's HCl addition, or sorry, HBr, here's HCl. Okay, now we're putting the alkyne in the middle of the molecule. Okay. Now we're putting in the middle. So in this alkyne, this is primary, this is secondary carbon, correct? Even though it's sp at the moment, flat and so forth. But when you do the reaction, there's gonna be a difference on stability. Here is both secondary. It's right in the middle of the molecule. You can't tell anything. So when you add, this is HCl and carboxylic acid. So you add HCl, it adds to it, and it's always going to add this way over here. There's a second equivalent, same thing, the chlorine is in the same position because it's a more stable carbocation. This one directs this chlorine, now directs the next one be in the same position, and you get this here. 3,3-dichlorohexane. So the chlorine is always going to be in the center here. Well, this is symmetrical molecule. They're both going to be on the same carbon. Everyone okay with this? Everyone understand why this is called Z? Remember we did this EZ system? Cis and trans are easy, or easier, is on the same side of a ring, but also in a molecule. There's hydrogens there, that's where the cis-trans comes from. But when they're not all hydrogens, right, there's 2 different groups here, 2 different groups here across a double bond. You look at the priority, this chlorine is higher priority than this one, across on this carbon, priority 1, priority 2. This carbon over here, which is a bigger group, CH2, CH3, or H? CH2, CH3, so the 2 largest groups are on the same side of the double bond, so it's a Z. So the other side is an E. We already did that. Okay, just a reminder here. Okay. Triple bond, the bromine, the You get the 3-member ring, the bromine does anti, so you get them on 2 different ones. You add bromine again, same thing, you get a 3-member ring, the bromine adds, so you get 2 equivalents. This is Br2, this is not HBr, this is Br2. Br2 does this 3-member ring intermediate, ammonium ion, right? When it's HBr, you don't get this, it's just an H, then you get a plus, then the Br comes in and attacks, Br minus. So we get to this reaction.